All right. So we're almost done. Chapter 12. On Friday, just quickly for the recording's sake, um, we talked about limiting reagent and yield. Where am I? I think I put those up. If you have a question about any of those, I can go over one or two of those shortly. Even though there's 4 and 5. Limiting reagent is the idea that you run out of something first, regardless of how good you can do. I used this example with coins. 45 cents, no change. You can do 5. You're limited by the number of dimes. Or if you have 10 loaves of bread, 2 gallons of mustard, and 4 slices of ham, the amount of sandwiches you can make is limited by the amount of ham you have. In terms of chemistry, we want to figure out which number of moles runs out first. There's a couple, like I did moles of each one. In reality, you can do one and do a conversion. But we do that. We figure out which one runs out first. In this case, it was chlorine runs out first. So we do our subsequent calculation with chlorine and get 144 grams of HCl. We also talked about the 3 types of yields. Actual yield, you mix some stuff together, you get something out. That's your actual yield. Your theoretical yield is your stoichiometric quantity based on your calculation. So I kind of did the example with that question before. If you mix those 2 quantities together and you get 135 grams of HCl, that's your actual yield. Your theoretical yield is your stoichiometric quantity, which we calculated. So no matter what, you're not going to have agreement here. Your percent yield is a percentage. I got 135 out of 100 possible, 144. So that gave us a percentage yield of 93.75. Today I'm going to go over this one here. What is the actual yield? What is the theoretical? What is the percent? If you start with 9.73 grams of aluminum, how much copper would you expect? And that's kind of the end of that. I do want to check. Did anyone have any questions about any of those 6, if you did them all, or any of them? For those of you who were here and what? Well, oh, if you, I didn't record it, so yeah. Those are the equations in there. I think they're updated in the file anyhow. But the answers are there. Crickets, crickets. So 6 grams of copper is produced when 3.92 grams of aluminum are reacted with blah, 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 according to this reaction. What is the actual yield of copper? Well, it tells us 6.78 grams of copper. So that is our actual yield. Our theoretical yield has absolutely nothing to do with our actual yield. And most people's issues with a yield calculation is the fact that you're given 2 numbers and you get this confused into, okay, I need to do something with it. This is produced when 3.92 grams of aluminum are reacted with excess copper sulfate. How much would you expect? This we have to calculate, and that's what this is for. And then we'll talk about the percent. So ignoring that bit, 3.92 grams of aluminum. Of aluminum, we want to know grams of copper. That this is our stoichiometry. I don't want grams of aluminum, so I'm going to put it on the bottom. I want mole of aluminum. Your first step is always converting grams to moles. Aluminum is 2698. And then that cancels with that. I don't want moles of aluminum because I want copper. So that goes in the bottom. We want copper. So then we go to our balanced equation. Copper is way down here. We get 3 moles of copper out of every 2 moles of aluminum that go in. Moles of aluminum cancel with moles of aluminum. Well, we've got the right stuff, copper and copper, but we don't want moles, we want grams. So grams of copper in, I think I used it somewhere up here recently. 63.55. That's what I thought. Just had to double check. It's Monday morning. Moles of copper cancel with moles of copper. We have the right units. We pull out our handy dandy Windows calculator. 3.92 divided by 2690. Whoa. 0.98 times 3 divided by 2 times 63.55 as we go all the way across. Divide by the molar mass, multiply and divide by stoichiometric coefficients and multiply by the last molar mass. We get 13.9 because that would round grams of copper. So if this reaction went all the way to the products, you should get 13.9 grams of copper. So this is the calculation one. This is here's your number. You are never going to calculate an actual yield in a question because you're not actually doing any chemistry. So if I want to find my percent, actual over theoretical, because I don't want to write the whole thing out, times 100, 6.78 grams divided by 13.9 grams, somewhat redundant, times 100. Whoa. 6.78 divided by 13.9 times 100, because 48.8. And that's what a yield question is. You don't do a lot of them in high school chemistry that I can think of, unless, because I missed some labs last year in chemistry 12 because I missed 3 weeks of school. This last part, if you started with 9.73 grams of aluminum, it's just repeating that calculation and figuring out, like, you're multiplying everything. Come on, fingers. If you started with that, you should end up with 34. And your percent yield is going to be significantly worse. Those are questions in the book about yields, but it's just, for now, this is what they are. This is the idea behind them. The next chapter, technically we need to look at chapter 14, which is the gas laws, but it doesn't really kind of flow with the rest of the stuff. So I always do 15, and 15 is, even in school, not even a full class, because 15 is a lot of, it's conceptual stuff. So I posted that. I've added a couple things over the years. 16 is concentrations, which is kind of a mole calculation, but it links 15 and 16 um, are kind of useful together. And then we'll talk about, after we do gas laws quickly, the kind of final calculations. And the last thing that we'll have any um, assignments with will be, there might be a question from chapter, 15, a couple questions from 16. Um, I do need to put one up for stoichiometry, which I found some old stoichiometry quizzes, so I'm going to put one of those, that'll be like 3 questions up today. So water, we call it a universal solvent because a lot of things dissolve in it. It's not really a universal solvent because universal implies everything will dissolve. So it's kind of a misnomer. Water is polar and it will dissolve soluble ionic compounds, as well as anything that's a molecular compound that's polar. So this goes to what we talked about, the polarity of a molecule. The oxygen is kind of the negative end. It's attracted to the positive end of other hydrogens, and we can kind of draw these in giant clusters. And there's people who actually will orient a whole bunch of water molecules and calculate that interaction and the distances and just build bigger and bigger clusters. Water makes hydrogen bonds, which is not a chemical bond, so to speak, but this hydrogen bond is this interaction. That was a really bad arrow. That's what I was going for. Um, this is why water has surface tension. It's why water has a low vapor pressure. Um, why it has a high boiling point. And it's because of this, water is very different from anything of its size. So water is H2O. If I go across the hydrides of that row, BH3, CH4, NH3, then we have water. The HF is a little bit kind of sketchy. That's a gas. That's a gas. Ammonia on its own, if you go to the store, you're buying a solution of ammonia dissolved in water, but if you have just straight NH3, that's a gas. And oh, is it still? I used to have a picture of like the relative boiling points. All of these boil significantly below 0 degrees Celsius. Like you're talking about like 100 degrees below zero. And this boils at 100 degrees above zero because these hydrogen bonds are so much stronger than any interaction that can go on in those kind of hydrides. It has a high heat capacity, which means water takes a long time to change temperature relative to things that are similar to it. If you put a pot of water on a stove, it takes a while to boil. If you have a giant body of water, like the Bay of Fundy, well, what? It's been about 15 degrees, give or take, for the last few weeks. If you go into the Bay of Fundy, go down to Alma or St. John and get in the water, it would be ungodly cold still. Even though the air temperatures have warmed up, I would say we haven't had snow in a while, but it's been a week. The best time to swim in the ocean is usually August, September, because it takes that long for all of the water, because there's such a ginormous volume of it, to heat up. And the water is usually warmer in October than it is in June because it takes a lot longer for water to um, get rid of all of that heat. which there's a whole section in Chemistry 12 about thermodynamics and that sort of stuff. Um, it has a low vapor pressure, which is linked to its high boiling and high melting points. A vapor pressure is the amount of gas that kind of sits over a liquid. Um, Ammonia has a relatively high vapor pressure. You smell it over top of a liquid. Um, what's another example of? Usually things that you can smell have higher vapor pressures, not that water has an odor. Um, Water is one of the few things that becomes less dense when it freezes. This is why ice floats. It's because it ends up with this rigid structure where everything gets all sorts of spaced out. Water is pure water, which is only H2O, which very few of us have access to, is a non-electrolyte. Because when ions are present, in water, we get a good electrolyte. For water, like tap water, has stuff in it. To get pure water, you have to go through a quite exhaustive process of distilling and deionizing, and it's quite complicated. When we talk about solutions, we need to know three things. A solution is a homogeneous mixture. So this is something we kind of went over quickly at the beginning of the year. I think it's been a while. A homogeneous mixture is the same throughout. So like pop is a homogeneous mixture because it's in theory the same all of the way through. Vegetable soup, not so homogeneous because you take a spoonful of it, you could have different amounts of different things. So a solution, the solvent, is what does the dissolving, which what we're going to talk about is water. The solute is what there is in less. So if we think about pop or juice or Kool-Aid, the solute is sugar. So this is the solute, solvent. So there's all sorts of different types of solutions. A solid in a liquid. In water is your classic example. You take something and dissolve it. A liquid in a liquid, um, the probably best one that is the most common, ethanol or alcohols in water. Making hand sanitizer is a whole bunch of alcohol in water. A gas in a liquid. Uh, Carbon dioxide or water or oxygen in water. Carbonated drinks. You dissolve, or the companies dissolve carbon dioxide in water. They put a whole bunch of it in, and then it can come out. Another kind of example, if you've left a bottle of water with the cap on, sitting on a table overnight, there's usually all sorts of bubbles around the outside when you pick it up in the morning. That's the oxygen that was in the water. It's dissolved in water, which there is oxygen in water. That's how fish breathe. That comes out of solution. An alloy is a solid in a solid. Um, Stainless steel is a little bit of carbon in iron. You do it, you melt it, and then you bring it down. Gas in a solid. You can get gases trapped in rocks. That's far and away the least common. Then this is an interesting question. Is air a solution? Well, for air to be a solution, we have to have a solvent and a solute. Well, air is, give or take, 77% nitrogen. I think it's about 18% oxygen. So that's 80, so that's 95. Other gases, carbon dioxide, methane, argon has a surprisingly higher percentage of in air. So is air a solution? Well, if we think about it, it can be considered a solution. What would be the solvent? If we consider it a solution, nitrogen would be the solvent because it's the most. And then we dissolve oxygen, gases, you can be considered the solutes. Water dissolves ionic compound. The rule for solubility is generally like. So what that means is not polal, because that makes absolutely no sense. Polar solvents. Oh, if I actually follow through. Polar and ionic. Nonpolar dissolves. So the typical kind of water is your typical polar solvent. Oil, like vegetable oil or canola oil or any of those, is nonpolar. Oil and water don't mix. Oil and vinegar salad dressing, if you go up into your kitchen and you have those, they separate after a while because oil is nonpolar, vinegar is a solution of acetic acid in water. Those don't mix. If you want to put them on your salad, you shake it up and they mix to a point, but there's still all sorts of bubbles and all of that. Salt is ionic, so salt will dissolve in water. Salt doesn't dissolve in oil. So when I say it's a class, it's like, yeah, it's a class in an hour. Eeny, meeny, miny, mo. Do I want to stop here and then finish these three tomorrow? Yeah, we'll do a little bit more. Ionic compounds are generally called salts. Any ionic compound is a salt. Salt at a store is one of the most common salts, which is sodium chloride. So if I have sodium chloride, I have an infinite lattice or array of these types of ions, and they're all stuck together. Well, sodium is positive, so it attracts negative end or the oxygen end of a water molecule. And you get a whole bunch of these kind of surrounding the sodium, and they start to pull it apart. Chloride is negative, so the same thing but in the opposite direction happens. You get the positive end, and you get this interaction between those. And basically water rips this apart. And salts will dissolve if the attractive forces of the water molecules, which are these interactions in here, are stronger than the binding forces between the two ions, or if it's like sugar. Some things are not soluble. We've talked about that. Lead 2 chloride. Those are two common ones. The forces that hold the silver and the chlorine and the lead and chlorine are so strong that no matter how much water you have, you can't pull those apart. Water does the same idea to polar molecules. Methanol is, well, because you've got these lone pairs here, and this end is polar, I can have hydrogens and it will dissolve. Sugar, has, if I did any bit of biochemistry, I would be able to draw the structure of sugar, but sugar has a whole bunch of these OH bits that water can interact and make. How it does this is hydrogen bonds. So anything with OHs tend to be very soluble. Methanol, ethanol are actually miscible with water. They don't. Um, it's more than dissolving. Water doesn't dissolve nonpolar molecules because there's no charges or polarity to interact with. Water must be attract, or water molecules attract each other and separate from the nonpolar molecules. Nonpolar are held together by this thing we talked about called dispersion forces, which are fairly different. Um, so the attraction between nonpolar things is similar, so that's why those will dissolve. That's why you can dissolve different, what are some, carbon dioxide will dissolve in oil. But we'll stop there. We'll talk about electrolytes. We're mainly concerned about water and what happens in there. We'll finish that. We'll talk about kind of checking types of compounds, what is in solution, and we'll go through these sorts of things tomorrow. But that seems 9:30. I don't want to keep anyone too long. I will update. Okay, you're being silly. That and chapter 12. I'll find some questions for chapter 12 and or for an assignment for those. And that's where we'll stop today. Sound good? Das ist good. I hope everyone enjoyed the wonderful weekend. Any questions? If not, I'll see some of you in half an hour and some of you tomorrow. Bye.